So in common emitter mode, only all current, voltage and power is gained. Or amplified. Therefore, common emitter mode is more preferred. So now there might be a doubt about what is this power gain, what is this current gain and all, right? You might have an idea like by giving a small amount of current, let's say by giving 1 milliampere of current, we can get 100 milliamperes of current. So that is not the idea. The idea is we have two different circuits. For example, we have a circuit for base emitter. Base emitter has one circuit. Collector emitter has one circuit. By sending 1 milliampere of current, we can get 100 milliampere of current out of this battery. Okay, actually the current is not produced somewhere. By sending this amount of current, we can control the current flow in the output. So here we have a current gain. By sending 1 milliampere, we can take 100 milliampere out of this battery. Okay, so that is a current gain. Similarly, if we apply a voltage of 0.7, this side we may get 5 volts. So that is a voltage gain. By supplying a small voltage, we can get a larger voltage on the other side. So if there is a current gain and a voltage gain, obviously there will be a power gain. Is the idea clear, Shahama? What does this gain mean? Not producing current suddenly, it is actually controlling the current by sending a smaller current. By a smaller current, we control a larger current. Did you get the idea? So next, representation of voltage difference. Next topic. Representation of voltage in a BJT. So this one we call the collector voltage. This is the emitter voltage, and this is the base voltage. If we show using an arrow, this is voltage of B respect to E, and this arrow shows voltage of C respect to B. And here, this is voltage of C respect to E. So from this, we can get an idea that voltage of C respect to E can be written as voltage of B respect to E plus the other way, right? Voltage of C respect to E plus voltage of E, voltage of, 1 minute. Sorry, this is B, right? Voltage of C respect to B plus voltage of B respect to E. Okay. CB, BE, if we add these two together, it should give the voltage across VCE. Next topic, characteristics of characteristics of BJT in common emitter mode. We have three characteristic graphs. First one is the input characteristic. Input characteristic. Input characteristic. So input characteristic, we input VBE voltage. So this is the common emitter, right? Common emitter. So we input a voltage between the base and the emitter. So that is VBE, that is the input, and based on that input, we are going to draw what will be the IB current. So during that we will have a VCE. So if we draw the characteristic for VBE versus IB for a certain voltage, up to a certain voltage, there is no IB current. There is no any IB current. And then suddenly the IB current increases. The IB current increases. So it is just like a normal diode. And here it's around 0.7 voltage. So when the BE region, when the base emitter region is forward biased, current will start to flow. Until then, there is no current IB. So that will occur at around 0.7. So if you want a complete plot, we have to maintain VCE constant. VBE versus IB is plot by maintaining VCE constant. So if we plot the same graph, for another value of VCE, it will be like this. Okay, if VCE increase, it will come down. I mean, the voltage will VBE voltage will come larger. So we don't need that graph. This is sufficient. This single graph is sufficient. That is the input characteristic. Second, we have the transfer characteristic. Second, transfer characteristic. So in the transfer characteristic, we are talking about the relationship between IB and IC current. IB and IC current. So if we plot IB versus IC, if we plot IB versus, sorry, IC versus IB, initially when there is no IB current, there is no IC current. For small value of IB current, still IC is almost zero, and then suddenly it increases, and after that it remains almost constant. IB is almost zero, and then increases, and then remains almost constant. So here, this region of the graph, we call it as the cut-off region. This is the cut-off region. It is just like switch off because there is no current flow, cut-off region. And this, we call this region as the active region. So this is the active region. Active region. And beyond this dotted line, we call this region as the saturation region. Saturation region. For different values, for different values of IB, different values of IB, corresponding IC value is measured and IC versus IB is plotted. For IB equals 0, IC is equal to 0. And this is known, and this is known as the cutoff. And this is known as the cutoff region. Similar to switch off. Similar to mechanical switch off. Mechanical switch off. And we have an active region, right? Here, IB and IC are proportional. Active region of the transistor or the active region of the BJT is used for amplification. Used for amplification. Since IC proportional to IB. Since IC proportional to IB. Or we can write that IC is equal beta times IB. Can you remember beta? That's the current gain. IC is equal beta times IB. Because for a small current, let's say we have a variation like this. If IB is varying like this, then IC will vary like this, right? Amplified. Only that's the difference. The shape and everything is preserved. That is why we can use this one for amplification. This is multiplied by beta times. At saturation, for any value, of IB remains almost of IB, IC remains almost constant. Almost constant. So there is no variation. So this is similar to mechanical switch on state. Similar to mechanical on state. Mechanical switch on state. Okay. So I'll explain why don't need to write this. I will just explain. Now we have three regions: cutoff, active, and saturation. For cutoff region, we have connected this to the output. We have connected this bulb to the output of the transistor. Okay. It is connected to the output of the transistor. If IB current is 0, then IC current is 0. Therefore, this bulb won't work. This bulb won't work. Therefore, it is just like switch is off. And for saturation, it is just like the switch is on. Current will flow. Therefore, the bulb will glow. Then what about this active region? This active region also, there's a current flow, right? There's a current flow. But why we are not using this active region as mechanical on state? The reason is, now in case of saturation, even though there might be small fluctuation in IB current, IC current remains almost constant. It doesn't change. But in the active region, if you have slight variations in IB, it is amplified and you can observe it in IC. So will the bulb glow continuously? Instead of glowing continuously, instead of the bulb glowing continuously, it will blink, right? It will blink according to this pattern. That is why we are not using active region for mechanical on state, mechanical switch on state, but we are using the active region for amplification purpose. Is that idea clear? Why we are not using active region for switch on state? How many you get the idea? Why we are not using active region for mechanical switch on state? Good. Okay. So now this is the IB versus IC character. IB, IC. So this is the transfer characteristic. I said that cutoff is similar to switch off and saturation is similar to switch on, right? But active, we are not talking about switch on or switch off. The reason is, let's think we have a bulb. The terminals of the bulb is connected to the output. It is connected to the output of the transistor. Okay, it is connected to the output of the transistor. When there is IB current, when IB current is 0, IC current is 0, therefore IC current is 0, bulb won't work. Switch off. And now let's consider a situation where IB current is huge, that IC current goes to saturation. Okay, IC current is now in saturation. During that, if the IB current is varying like this, IB current is increasing, decreasing, increasing, decreasing, will that bring a huge variation in IC? No, right? You don't at least observe it. It's almost straight. So IC current remains constant. Even though there's small variation, IC current remains constant. Therefore, this bulb will glow continuously. Up to this, is it clear, Shahama? Before we go to active, are you clear with saturation? Why we can use saturation as switch on? Now, let's think the IB current is not that sufficient to go into saturation. Now it is in the active place, active region. And we are not having a constant IB. Instead, I am having an IB that is varying up and down. It is increasing, decreasing. What can you tell about IC? During the same time, IC will be varying. During the same time, IC will vary. The variation is huge. For this small variation in IC, you observe a large variation in for small variation in IB, you observe a large variation in IC. So the IC is connected to this bulb, right? So this bulb, instead of glowing continuously, it will start to blink. So it is not like switch on, right? It is just like a loose connection. That is why we are not able to use active region as switch on. Did you get the idea? But we can use that one for amplification purpose, because look, For small variation in IB, you get a large variation in IC, the same pattern. Okay, that is what we mentioned in the previous note. So third character is the output characteristic. So output characteristic is drawn between IC and VCE. So it is also like increases first. After that, there is very small or slight increase. It remains almost constant. To obtain this graph, we must keep IB constant. For a constant value of IB, we get this graph. As VCE increases, from 0, IC increases rapidly, and then remains almost a constant. Or increase slightly. No, let's say it remains almost constant. That is enough. Now, this graph is drawn only for a single IB current. If we draw the same graph for multiple IB current, we get a graph like this. So this value is for IB is equal to 0. IB equals 0. Then in this direction it increases. Let's say this is IB equal 10 microamperes. This is 20 microamperes, and so on. Okay, it increases. Now in this graph, this region we call as the saturation region. We call this one as the saturation region, and the region below IB is equal to 0, that is the cutoff region. And the area between these lines, this region over here, this is the active region. Okay, So this graph, you won't sometimes understand now. For now, you just remember the regions. You might not get the idea of this graph. When we discuss about the application of BJT, then you will understand uh, why this graph is important, how to get the information from this graph. Okay. So once you have noted, let me know. Okay, so inshallah, in the next class, let's discuss some questions and how we can use this transistor as a switch and as an amplifier. Okay, with that, we can complete this transistor part and start FET, junction field transistor. Okay, Shaman, in the meeting. Hope there's no doubts. Do you have any doubts? Do you have any doubts? Okay, Assalamu alaikum.